All right. So got a lot to get through on this one, so I'm gonna blaze through some of the early stuff, uh, which is kind of a duplicate of what we've already been through on the others. So there's the green bank dish. Um, done some of these I did these observations for the mapping exercise the same way we did the integrated spectra observations. The only difference is we were looking at galaxies that were nearby enough that their angular size was large enough that we could actually resolve spatial information. So, so what we would do is we would take the spectra the same way. We would do uh, the analysis in Excel the same way. But then what we did is we would look at the corrected spectrum and we would look at was there a single peak in the spectrum that was kind of winning out over the others, or was it more of like a broad, flat, you know, spectrum? Um, and then that would determine whether when I was doing the when I was doing the spatial plot, whether I would give a value to that point of the average of the whole spectrum, uh, or whether I would just give the peak value, the velocity at the peak value. Um, and the way I would do this, the average on the spectrum is I basically multiplied the uh, the the vertical scale by the horizontal scale, and then divided by the average of the vertical scale, and then that would give me a point that would be somewhere that was sort of like the geometric average of that. And I would only use that method if if the spectrum didn't have some kind of obvious peak that was higher than the others. So this was an early overlay coverage map of our M31 observations. And so I just basically started doing single points uh, within the disk of M31. Um, and this was kind of this was an early kind of a proof of concept. So what we did is we did a handful of observations, and what it was is we had done these observations before we even started doing this project, and I just pulled together all the observations that between myself and Andrew had done over the last year, and I placed them on the grid on the RA deck grid to see what we would find. And this I colored them on a red to blue gradient, blue being the most blue shifted and red being the most red shifted. And we this definitely showed that our method was working. And so it was sort of like an early test to see are we even going to pursue this? And when I saw these results, I was like, okay, we need to pursue this because this looks really promising. And so I did an early overlay of the optical um, on top of our Doppler plot just to kind of show how it matches, and you can clearly see the blue shifted side and the red shifted side are definitely, you know, on opposite sides of the disk, which is what you would expect. And then we started filling in more points, and this was really exciting when we started seeing this. And then so then I said, okay, let's do the same thing with M33. And this was the early result. And I just thought it looked amazing. I mean, it's just like, wow, this really, you can see the rotation, you can see the axis of, you can see the central axis where, from our perspective, the motion becomes completely tangential. So you got this line of transition between red and blue shift. Um, and there's an overlay again of the optical. And then, so I decided to work my way down the list. Did M101 next, IC342, NGC 2403. So these were early tests. This was kind of an early two scale picture of all of them, oriented with right ascension at the top as a horizontal axis and deck as a vertical axis. And then these are all to scale. And and I represented the half power beam width of the 20-meter dish there, so you can kind of see uh, as optical astrophotographers have mentioned, you can get spatial resolution within the the beam width of the antenna simply because it's not uniform. You do have a Gaussian distribution here, so that circle represents the half power point, right? And so even if you move within that, you get difference, and it's measurable, and you can actually get spatially separated information that way. So this was we had our observation plan to then expand out from where we initially started. And here's where the big reveal happens. So this is what we now have. So M31, I didn't fill in the entire disk, but because it was a lot of points, and I kind of wanted to prioritize the smaller ones. But you can definitely see one of the things you can see clearly is that the hydrogen extends well beyond the optical disk. This red oval overlaid on the plot represents the edge of the visible disk in the optical. So look how much farther it extends. So the way to interpret this, the upper left is average Doppler, the upper right is peak Doppler, the lower left is average intensity, and the lower right is peak intensity. Now I kind of favor the peak on both because they seemed to just give I think they represent the spatial information better. And then I actually did an overlay from an early a late 70s high resolution survey that was done. They had a contour plot of total power or of intensity, and then a content plot of Doppler. And I overlaid that on our results, and you can see the match is remarkable. It's really cool. Here's M33, and again you can see how far it extends beyond the visible disk there. And here again, there's another survey from I believe the early 80s with both intensity and Doppler overlaid on our data. Honestly, the Doppler of M33 is one of my favorite because I think it looks like a yin yang. It's I would I was going to talk to Rich about maybe making this into a t-shirt design. I think that would be cool. Uh, okay, and here's M101. And even with M101, we're getting spatial resolution here. And look at the way the contour plot matches with our intensity data here. It's remarkable. IC342 was the most interesting, I thought, because it extended so much beyond the optical, and it's very asymmetrical. And so I when I saw that initially, I I was kind of questioning the integrity of my analysis. And I noticed that the asymmetry was largely on the redshifted side, and that's the side that's this one tends is very it butts up right against the Milky Way signal. And so the redshifted side is kind of smeared into the Milky Way. So I thought, well, maybe this is an artifact of that it's just difficult to analyze because it's getting corrupted by the Milky Way, right? But then I looked at the contour plot from a professional survey and it's actually that way. It is asymmetrical. It just that's just the way the galaxy is. So that was super satisfying. Uh, and then NGC 2403, it's a beautifully symmetrical one. Um, and then there's the entire family, all five in a row to scale here. Uh, Total power on the top, Doppler on the bottom. Uh, and then again, we showed this in the previous one, but you have, you know, the orientation of the galaxy as far as how edge on or flat from our perspective the disk is will determine the width of the spectrum. Um, and then another thing we can see, so I did 3D surface plots of the peak velocity, and you can definitely see the telltale flat, relatively flat velocity profile across the disk, which is a, a telltale. I mean that's the telltale sign that dark matter is a thing because that the flat velocity curve indicates there's a lot more rotational velocity than can be accounted for from the visible matter. So the gravitational the gravitational force on the outer regions of the disk are way higher than what we would expect from the visible matter. So you can see that flat S curve for all of these. So that's yeah, that's pretty much the entire presentation. Now I guess I'll open it up for questions from the audience. So.
Any questions for Jason? Hey, Jason, how much time do you use both?
How much time? Sorry.
So how much dish time did it require to do this project?
Yeah. So quite a bit. So what that's one of the reasons why I was using very short durations on. I was basically using the shortest duration I could each on each spatial point. And so for instance, for M31 and M33, because they're so nearby and the signals are very relatively strong, I used 1 second on each point. And so basically end up with however many points multiplied times, 1 second. And I believe the credits are around 1 credit per second of something like that, about 1 credit per second on target. So in the case of M31, if we look at the number of points we have, let's see if let's go back to oh shoot. Let's so M31 we've got we're getting up to I think the 80s or the 90s by the time we were through. So probably somewhere in the realm of maybe a couple hundred credits for that one. So yeah, we definitely used several hundreds of credits to do these plots. Basically, the smaller galaxies ended up having to increase to maybe up to 4 or 6 seconds on target for each point. Uh, and this is one of the reasons too why I switched to using tracking mode rather than on off. And so I would only use one calibration point per observing session so that I wasn't, doubling my observation time for each point. Um, and so trying to be very thrifty because I wanted to have, use I was wanting to be frugal with the credits so that I could, gather a lot of spatial points with and not waste a bunch of credits. So um, I think when we got down to, for instance, when we got down to NGC 2403, we were needing like 8 seconds, 8 to 10 seconds on each point to really get enough a strong enough spectrum to work with. So, but the smaller ones required fewer points as well. So, um,
Thank you, Jason. Any other question? That's good.
Hi, Jason, thank you. Did you see any problems with radio frequency interference?
not really. I haven't really had a lot of problems with RFI, specifically on um, hydrogen line spectra um, and capture, and it may be due to the fact that well, for one thing, we're doing off-target sky calibration, so you're getting observations from slightly different points in the sky and slightly different times. Uh, so, but no, I didn't really have much trouble with RFI. Um, I know RFI tends to be an issue in L-band, but I think maybe it's probably more of an issue if you're doing um, continuum observing. But spectral observing, if there was RFI, I'd be able to kind of uh, blank it out if I saw it. But no, I didn't really have too much trouble with that.
Thank you, Jim. Other question?
Hey Jason, could you go over again the velocity, I think it was like the velocity curve for M31 and just how it related to dark matter? I understand like the relationship between, we know it has to fill in the gap between the real matter and the galaxy. But how did that relate to the velocity curve? I got a little confused.
You muted yourself, Jason.
Oops, you muted.
You're still muted?
Okay, yeah, let me share my screen again and I'll if I can do this. So we didn't really have a plot like we did for M33 of the curve, but you can see it on the surface plot if you kind of look at I'm gonna zoom actually. Can you guys see that?
I might have meant M33. Sorry, whichever one. I think it was slide like 30s something when you had the
36.
Yeah, 36.
Oh yeah. Okay, there we go. So what you see and I'm assuming, can you guys see the plot?
Yes.
Yeah.
Okay.
We see your cursor.
Yeah, so if you were looking purely at the visible matter in the galaxy, you would expect it definitely shows that, you know, there's a concentration of matter in the center in the center of the galaxy, and then it spreads out as you go out in farther into the disk, right? So if you were looking at what Kepler's law would look like, you would see a plot that would where the curve would look more like this, right? Where it would the velocity would slow down as you got farther out. But what we see is it doesn't if it stays flat, even out to the edge. You still have the velocity kind of stays high. And the only thing that we know of that would account for that is something is causing a lot more gravitational pull out at the edge than what can be accounted for by the mass of the visible matter, because we're not seeing a Keplerian curve, like basically almost like an exponential drop as you go out. You're seeing basically a flat a flat profile where the velocity is just staying almost constant as you go out from the center.
Awesome, thank you so much.
Yep.
Any questions online? Hey, Jason, I did have a question about basically the beginning of your presentation. How did you calculate, like, what was the representation of each cell? Because I noticed each cell, at first I thought it was your beam width, but each cell was not a beam width. So how did you calculate what represented each cell?
Yeah, so it was kind of I played around with it a little bit. I knew that I wanted to go smaller than the beam width because I figured that we could get resolution within the beam width, but it was kind of an arbitrary choice. And so I think what I did is I think it was kind of an arbitrary choice where I didn't want to take too many points and end up having to waste a bunch of credits just to get, any kind of mapping of, because M31 is fairly large. And so it was kind of like this trade-off between, okay, what resolution do I think I can get um, versus how many points do I really want to mess with, And so I kind of settled on this. Uh, I think let's see here. Let me look at the mapping. So I think I settled on using separations in right ascension of just 1 minute apiece. And then in declination, I did 15 arc minute separations. So basically a quarter of a degree. And it was kind of, like I said, that was kind of an arbitrary choice. And then once I used that on M31, I just stuck with that same scheme for all the others because I kind of wanted to do apples to apples comparison. And so yeah, so then when I planned out the others, I just used that same scheme. And now what you'll notice though is the right ascension is not they're like lines of longitude right on a sphere. So as your declination gets higher, the right ascension lines get closer together. And so I had to do some scaling based on declination to kind of make to make the plots kind of have the right aspect ratio. So I was trying to make it so that the aspect ratio in right ascension and declination was roughly 1 to 1. And I kind of just did the trig to figure it out, and then just kind of scaled the aspect ratio of the column widths in Excel to make it so that it was roughly as close as I could get, so that the aspect ratio always matched. And that way, when I got to where I showed them all to scale, that's the method I use. So declination, they were all 1 to 1, but the right ascension I had to kind of scale based on what the declination was, and it was a cosine function, so.
Gotcha. All right, thank you very much. Thoughts, questions, any more? Well, thank you again, Jason.
Thank you.